5.4. The proofs for these formulas, we can come up with two of the formulas and then use those two to come up with the rest. Where they come from, drawing triangles on the unit circle and keeping track of little pieces. It's not difficult where they come from, and they go through it in the book, but I don't think that knowing where they come from really helps us understand them. So what I'm going to do is just write out all of these formulas, and then we'll talk about how we use them. My point with the formulas, the identities, the things that we'll do in these last two sections is that you have some familiarity with them. You know that they exist. They are not quite as what do I want to say, foundational as the other identities we've worked with. So I want you to know that they exist. I want you to have some familiarity with them, but they're not quite as I don't want to use the word importance, but that's about as close as I can get. They're not quite as important as the other identities, but they are very, very useful. So our formulas. What we're doing is finding the sines, cosines, and tangents of angles that we're adding together. So we're going to find the sine of u plus v. My v's have this little tail on them, so you can tell I'm using these apart. Sine of u plus v is sine u cosine v plus cosine u sine v. It is not sine u plus sine v. Students make this mistake every year. Please try not to make this mistake. I'd have to draw, it comes from drawing triangles on the unit circle, and we're adding pieces of triangles together, so it's more complicated than this. Sine u minus v. Sine u cosine v minus cosine u sine v. So the sines and cosines end up mixed together. Our cosine formulas. No, what I'm saying is students they forget that the formula is complicated, and they say, oh, sine of 25 plus 40 is the sine of 25 plus the sine of 40. And I'm saying don't do that. There's more involved than just taking the two pieces. So I'm saying this doesn't equal sine u plus sine v. So it's all of these are mixed together. So sine u or cosine u plus cosine v. Cosine u cosine v minus sine u sine v. And our cosine difference formula cosine u cosine v plus sine u sine v. So notice with the sine sum and difference formulas, the plus and minus are the same on each side, and with the sines and cosines are mixed. The cosines, the plus and minus is opposite, and the cosines and sines are together. And for this one, you need to remember that cosine of u plus v does not equal cosine u plus cosine v. It's more complicated than that. And then our tangent formulas for the sums and differences, we can use sine u plus v over cosine u plus v and simplify. It takes a fair amount of work. Same thing for the difference formula. So our tangent sums and difference formulas. Tangent u plus tangent v divided by 1 minus tangent u times tangent v. And the difference formula, I get tangent u minus tangent v. Over 1 plus tangent u times tangent. And again, tangent u plus v does not equal tangent u plus tangent v. So what I want to do today is just go through several examples of how we're going to use these sum and difference formulas. So questions on our formulas. All the rest of the formulas that we'll talk about for the rest of the semester we can get from these formulas. So these are fairly important for the formulas that we'll use. Tomorrow we'll talk about double angle formulas and half angle formulas, and they all come from these formulas. All right, so let's take a look at some examples. So the types of problems that you'll be asked to do. We want to find the exact value of the sine of 15 degrees. Well, the words exact value are a hint. We're not using our calculator. It has something to do with fractions, unit circle. So what a problem like this is asking us to do is we want to find unit circle angles that we know are on the unit circle, that add or subtract to give us 15 degrees. And then we're going to use a sum or difference formula. So what familiar unit circle angles add to 15 or subtract 15?
45 and 30.
45 minus 30. So 15 degrees is 45 degrees minus 30 degrees. So what we're looking for here is the sine of 45 degrees minus 30 degrees. And we're going to use our difference formula for sine. So this equals the sine of 45 degrees times the cosine of 30 minus cosine 30 degrees sine 45 degrees. And now this turns into a unit circle problem. Cosine well, that's right, isn't it? Oh yeah, I've put these backwards. Thank you. Otherwise I have sine of 45 twice, right? Thank you. Alright, so now we have a unit circle problem. Now that we've gotten this correct. Sine of 45 degrees is square root of 2 over 2. Cosine of 30 degrees square root of 3 over 2 minus the cosine of 45 is the same as the sine of 45 minus square root of 2 over 2. The sine of 30 degrees 1/2. When I multiply straight across. When I multiply radicals, I can multiply underneath the square root. So this is going to be the square root of 6 over 4 minus square root of 2. Square root of 2 times 1 is just square root of 2 over 4. And my exact answer is square root of 6 minus square root of 2 over my common denominator of 4. So the sine of 15 degrees, the exact value of sine 15 degrees is square root of 6 minus square root of 2 over 4. Kind of nifty. So this really expands the number of angles that we can find the exact values of sines and cosines for. These aren't as nice as our unit circle angles, but we can figure out the exact values. Questions on that example? Yeah.
So why is it sine 25
So the reason that it comes out this way, again, it comes from if we draw triangles on the unit circle and subtract the angles, it's adding and subtracting the different pieces of the angles, and that in the process of doing that, one part of the triangle is the y coordinate of one and the x coordinate of the other. So you end up with the parts mixed together. So it comes from the formulas again come from drawing triangles for u and v, and then for u minus v, and looking at the parts and coming up with quantities that represent the different sides of the triangles and adding those together. And it just turns out like that. Okay? Without going through the process, that's about the best explanation that I can get. All right, let's look at another example. All the textbooks like this particular example. We want the exact value of the cosine of 7 pi over 12. So we're looking for two unit circle angles that add or subtract to get us 7 pi over 12. Anyone think of what those angles could be? Pi over 6 and pi over 2? So let's look at pi over 6 and pi over 2. So I'm going to multiply this by 2 over 2 to get my common denominator. So this would be 2 pi over 12. And this would be 6 pi over 12. So we're off by 1 pi over 12. That was close. That was a good guess. Anybody have another? Pi over 3 and pi over 4. 7 pi over 12, you were close, exactly, but pi over 12 is pi over 3 plus pi over 4. 3 plus 4 is 7, and 3 times 4 gives us our common denominator of 12. So the textbooks like this one because of this nice look. So what we're finding here is the cosine of pi over 3 plus pi over 4. So we're going to use our cosine sum formula. That's going to be the cosine pi over 3 cosine pi over 4 minus sine pi over 3 sine pi over 4. Cosine of pi over 3 1/2. Cosine of pi over 4 square root of 2 over 2. Sine of pi over 3 square root of 3 over 2 times square root of 2 over 2, and we get square root of 2 minus square root of 6 over 4. So when we're doing these problems, this square root of 6 shows up quite a bit because we have the square root of 3 and square root of 2 on unit circle angles a lot. Questions on that example? All right, let's look at one where we go the other direction. We're kind of using the formula the other direction. We want to find the exact value of cosine 78 times cosine of 18 plus the sine of 78 times the sine of 18. So what this problem is asking us to do is recognize the form of this expression, which one of our formulas does this look like? Cosine difference, right? So this is the cosine of 78 degrees minus 18 degrees. It matches the form of the cosine difference formula. Cosine of 78 minus 18 is the cosine of 60 degrees, which is 1/2. So this expression is equal to 1/2. The exact value is 1/2. So sometimes you'll be asked to recognize a form, move in the other direction. All right, questions on that example? All right, now we can verify one of our favorite identities. Verify that the sine of pi over 2 minus x equals a cosine of x. Well, we have a difference formula that we can apply here. The sine of pi over 2 minus x is the sine of pi over 2 times the cosine of x minus the cosine of pi over 2 times the sine of x. Sine of pi over 2 is 1. So I'm just left with 1 times the cosine of x. Cosine of pi over 2 is 0. And all I'm left with is cosine x. So now we're able to verify our cofunction identities using our sum and difference formulas. That's kind of nice. So now if you can't remember this, and you can remember your sine difference formula, you can verify that identity. All right, on this next problem, I want to set it up. We're not going to go through the process of doing the entire problem. I just want to talk through about the process of solving this next problem. So let's say we have an equation that we want to solve. We're asked to solve cosine of x plus pi over 4 minus cosine of x minus pi over 4 equals 1. So we want to find the values of x that make this true to solve this. So what process could we use? Let's look at this piece. What could we do to that? Well, this is a pi over 4, so you're kind of on the right track. And we have a sum formula for cosine. So we would use our sum formula here. We would write our sum formula out for the cosine of x plus pi over 4. And here, we would use the difference formula. And write that out. And we know that it involves sines and cosines of pi over 4. What's the sine and cosine of pi over 4? Square root of 2 over 2. So square root of 2 over 2 is going to be involved in there somehow. So we would write out our sum formula here for cosine, write out our difference formula, our minus formula for cosine, and then we would combine like terms. So we'd get sines and cosines, and we'd combine our like terms. Then we'd simplify. So we're going to combine like terms, simplify, and then get our trig function on one side of the equation. We know how to solve trig equations when we have a nice looking trig function. when we did all of that, we would end up with sine x equals negative square root of 2 over 2. After we combine like terms and simplified, this is what we would be left with. And we know how to solve that. So first we'd apply our sum and difference formulas, combine all of our like terms, and then we would simplify everything we have. So that would be our process.
And so we look at that again.
Well then, so to solve this, then now we look on the unit circle. What value of x gives us a sine of negative square root of 2 over 2, like we did on the quiz. We'd find x, and we'd find x. All right, I want to do two more examples. One using a tangent formula, and one that requires just a little bit more work. So we see the tangent formula once. We want to find the exact value. Anytime we see exact value, that should be a hint that it has something to do with unit circle when we're doing trigonometry. Of the tangent of 255 degrees. So we're looking on the unit circle for two unit circle angles that add or subtract to give us 255 degrees. So what unit circle angles would add or subtract to give us 255 degrees? Okay.
225 and 30.
225 and 30? So we could have lots of different answers. 225 plus 30, 270. Now, is 15 degrees a unit circle angle? No. It'd be nice if we could do it that way. It does work, but 15 degrees is in a unit circle angle. Did someone else think of some other ones? 300 minus 45. And what did we do in the last class? 210 plus 45, what we came up with last time. So we can use any of these. Which one do you want to use? 225 plus 30? Okay, so we're going to find the tangent of 225 degrees plus 30 degrees. So we're going to use our sum formula. Any one of these that we use, as long as we pick one that adds up the right way, is going to give us the same answer. We'll come up with the same answer no matter what. So we're going to use our tangent sum formula. So this is going to be the tangent of 225 degrees plus the tangent of 30 degrees over 1 minus tangent 225 times the tangent of 30. So what is the tangent of 225 degrees? 1? So that's nice. 1 plus the tangent of 30. We need to write that one out. Tangent of 30 degrees, sine of 30 degrees. Square root of 3 over 2. The cosine, 1/2. When I divide that out, I get square root of 3. So I get 1 plus the square root of 3 over 1 minus, this is 1, square root of 3. If you leave your answer written this way, I would be fine with that. I'm not going to ask you to rationalize this. If we did want to rationalize this denominator, what would we do to rationalize it? Multiply the top and bottom by 1 plus the square root of 3.
units.
Yes.
First bracket, is that 5 or 6? What's 30 degrees of each?
30 degrees is 5 or 6.
Yes, it'd be 100.
Did we do it backwards? So this should be 1/2 and square root of 3 over 2. So what does our answer come out to be? Square root of 3 over 3. So this should be a square root of 3 over 3 and a square root of 3 over 3. And then we would just change these to square root of 3 over 3. And we could multiply this out and rationalize that denominator. And if we do this, it comes out to be, if we rationalize it, 2 plus the square root of 3 is what it ends up. But if you write the answer in this form, there's enough places for mistakes and to make a sign error that to go from here to here really doesn't gain us anything. This shows that we know how to use the formula properly. All right, questions on that example? All right, next one, my favorite example. I just like these kinds of problems. They're nice. They tie a lot of things together. We want the exact value of cosine of u minus v if sine u is 5/13, cosine v equals -3/5, and both u and v are in quadrant 2. So we want to use this difference formula, but what are we missing? We're missing what u and v are. But when we write out our difference formula for cosine of u minus v is cosine u cosine v plus sine u sine v. We're missing sine v for this part, and we're missing cosine u for this part. How can we find them? Draw a triangle. Draw a triangle will get us the sine of v for this one. And we need another triangle to get the cosine of u for this one. So we need 2 triangles. We remember that these ratios always give us the sides of 2 sides of a right triangle. So we need 2 triangles. That's why I like this problem, because it brings us back to drawing triangles, which we did in chapter 4. And then we're also combining that with our sum and difference formulas. So let's draw a triangle here and I already made a mistake. We're in quadrant 2, so I'm drawing my triangle this way. So my x coordinate is going to be negative. So here's my triangle for angle V. Cosine V is -3/5. So the adjacent is -3 and the hypotenuse is 5. So what's my missing side here? 4. They gave us nice numbers. So sine V is 4/5. And then I draw another triangle for angle U. And we know that sine u is 5/13, so opposite and hypotenuse. And what's our missing side here? 12. This is a 5, 12, 13. And this would be negative since we're in the second quadrant. So cosine u is negative 12 thirteenths. So now I'm ready to write out my formula. Cosine u minus v. I didn't even have to find the angles. I could just find the sines and the cosines. Cosine u minus 12 thirteenths times cosine v, negative 3/5, plus sine u 5/13 times sine v, which is 4/5. So I get 36 65ths plus 20 65ths equals 56 65ths. And that's the exact value of cosine of u minus v. I love that problem. Two triangles, Pythagorean theorem, sum and difference formula combines all kinds of things together. All right, questions on that one? Okay. Homework. There we go.